Welcome back, where today we're discussing ant farms, because these things made a big impression on me when I was young. A colony of ants living in half a cup of sand enclosed between two plates of glass. Actually, I'm sure it was plastic, since we were kids after all. The ants do their thing, and by the next day you come back and they have done some remodeling. It looks like ant hills here and there. And if you were enough of a pest like I was, you might grasp the ant farm between your two hands and shake it so that the sand would all settle to a uniform level like this. Actually, I don't recommend doing this in real life. It drives the ants crazy. So this really is what in physics we call a thought experiment. But if you did this, the final height of the sand in the ant colony would be the average height of the sand that you saw before shaking it up. Now, let's do the same thing with a function graph of a function f. The average value of the function on the interval AB is what we want to define. And to understand this concept, you should imagine that the area under the curve is like the sand hills in an ant farm. When you shake it up and allow the sand to find its natural level, the average value of the function will then be the final height of the sand. In other words, the area under the graph of f is exactly the same as the area of the final rectangle, with the same base, b minus a, and height given by the average value of the function. And we're denoting that by f bar. Since the area of the rectangle is base times height, you can get a formula for the average value of the function. This says that f bar equals the integral divided by the length of the interval b minus a. My picture just shows a positive function f, but exactly the same formula works for any function f, even if f is negative, in which case the average value of the function can also end up being negative. This notion of average value or mean value is consistent with what we usually mean by average. In fact, this generalizes the usual notion of average. For example, suppose we check 5 students to see how many books they have in their desks, and we get a list of numbers 4, 7, 9, 4, 8. What is the average number of books per student? And you know how to find the average. You add up the list of numbers and divide by the number of students, which is 5. The answer in this case, 32 over 5, gives 6.4 books on average. So it's possible to compute this answer using our formula for the average value of a function. Draw a graph, which is basically a bar graph of the data. The function is defined between 0 and 5, and on unit subintervals, its values are the numbers 4, 7, 9, 4, and 8. What about the points between? So how do you define f of 1? Should f of 1 equal 4 or 7, or should it be simply undefined? Well, I've decided to show f of 1 equals 7 in my graph, although it doesn't really matter how you define the function at a single point, like at 1. If you change the value of the function at a single point, like at 1, it will not change the area under the curve. There's no area under that single point, so it won't change the area. It won't change the integral. Now, according to our formula, to get the average value of the function, you integrate. That's the area, which you get by taking a Riemann sum with n equals 5 subintervals, and that'll give the exact value for the area. And then you divide by 5 minus 0, and I think you get the same answer, 6.4. By the way, note that this function is discontinuous, but clearly this did not create any difficulty for us when it came to integrating it. It was clear what is the area under the graph. Now let's try a familiar continuous function, we'll ask for the average value of e to the x on the interval from -1 to 1. Write down the formula. The integral is the area under the curve. We also need to divide by 2, which is the length of our interval. Use the fundamental theorem of calculus. An antiderivative is e to the x, and you evaluate that between -1 and 1, and here is the answer. In the graph, I have shown you a rectangle with the same base as our region, also height equal to the average value of the function. And you should believe that the green rectangle has the same area as the shaded region under the curve. So far, we haven't stated any theorems, only a definition, the definition of average value of a function. But here now is a theorem. We've already seen something called the mean value theorem for derivatives. This now is the mean value theorem for integrals. I really want to say that this is more basic than the mean value theorem for derivatives. So what I mean is, when we're talking about average value of a function here, that's simpler than in the mean value theorem for derivatives when you're talking about the average of the derivative of a function. Now I'll clarify that distinction by comment at the end of the video. Anyway, here is the statement of the theorem. Suppose f is continuous on the interval AB. The conclusion is that there exists a point C in the interval where the function value is exactly the average of the function on the interval. So graphically it says the graph of f must intersect the top boundary of the green rectangle. This should sound to you like a very reasonable conclusion. Also, it should sound more like the intermediate value theorem than the previous mean value theorem for derivatives. But in any case, the three theorems are all pretty similar. And just like in the previous theorems, when we say that there exists a point C in the interval with a certain property, we don't mean only one such point. We mean that there is at least one such point C. In the example I'm showing you here, it looks like there's actually 5 points for C, which satisfy the conclusion. Now let's go back to example 2, and we'll verify the theorem in this case. We've already found the average value of the exponential function on our interval. And this being a continuous function, we're saying there has to be a point C where the function value equals this average value in the interval. And you can easily solve the equation and find that there's exactly one solution. And there can't be more than one actually, because the exponential function is increasing. It can't attain the same value more than once. Here I found the exact value for C, also a decimal approximation. Now let's have another look at example 1. In this case, the average value of the function was 6.4. Notice that there is no point C in the interval 0, 5, where the function value is exactly 6.4. In other words, what we're really saying is that the students had 6.4 books on average, but none of the students has exactly 6.4 books, just like no family really has 1.5 children. But this doesn't violate our theorem because our function is not continuous. So the theorem just simply does not apply in this situation. Let's move on to a third example. Now we're asking for points between 0 and pi where the sine function attains its average value. So first we have to compute the average value. Here's the definition. To integrate, use the fundamental theorem of calculus, evaluate our antiderivative between the two endpoints, and simplify. The average value is 2 over pi. That's about 0.637. Now from the graph, it should be believable that the area under the arch is the same as the area of the green rectangle. Now we need to solve for c, a point where the function value equals 2 over pi. And there are exactly two solutions, in this case, in our interval, as you would expect from looking at the graph. And here are the two solutions. I've written them exactly, and also numerical approximations correct to 3 decimal places. Now, so far, we have used integrals to calculate average value of a function. But this idea can also be used in reverse. I mean, if you have a good idea about the average value of a function, you can turn it around to understand the value of the integral. For example, consider the temperature, capital T, at various times little t throughout the day. How do you integrate this function? Well, if you know the average temperature during the day, you just multiply that by the length of the time interval. This is, of course, assuming that you happen to know the average temperature during that time interval. In any case, to understand what we're saying here is to illustrate knowing the integral is equivalent to knowing the average value. Either piece of information will tell you the other. Here's an example where you can use this idea. Now I'm considering the function f of x equal cos squared of x. And by one of the basic trig identities, this equals half times 1 plus cos 2x. Now the cosine of 2x oscillates with an average value of 0, so the whole function f of x on average is a half on average. And the average at least over each cycle. So for example, the integral of cos squared of x from 0 to 10 pi, you can just write down it's 5 pi. The same as the area of a rectangle of base 10 pi and height a half. So note that our function goes through 10 full cycles over the length of the interval. So the average value is a half over an interval of length 10 pi, so you just multiply and get 5 pi. Now let's use symmetry to help us with evaluating certain very special kinds of integrals. Here's a graph of a somewhat randomly chosen odd function, an odd function. Whatever it is, just because it's odd, its integral from minus a to plus a has to be 0. That's because whatever happens on the left side exactly cancels out whatever happens on the right side. So the net area is 0. Although the function isn't simply 0, on average it comes out to be 0. And if the average value of the function is 0 over the interval, then the integral is 0. Of course, this only works for intervals centered at the origin, which is to say intervals from minus a to plus a. And likewise, if a function is even, then the net area on the left side equals the net area on the right side. So the integral from minus a to plus a equals twice the integral from 0 to a. Once again, this only works for intervals centered at 0. But it's helpful to think this way because sometimes it's easier to evaluate the antiderivative at 0 rather than at minus a. All right, a couple more examples using symmetry. Here's a typical textbook problem to see who's awake In this case, you'll be wasting your time trying to come up with an antiderivative for this integrand. Don't fall into the trap. You're supposed to look at it and recognize that the integrand is an odd function of x. Since you're integrating from minus 8 pi to plus 8 pi, the integral is therefore automatically 0. Now here's a more typical example. Very useful to use symmetry. In this example, we're integrating a polynomial from minus 2 to plus 2. First, you can just ignore the terms with odd degree because they form an odd function. After deleting them, what's left is an even function. So the integral is just twice the integral from 0 to 2. And it's easy to write down an antiderivative. Evaluate at 2, then multiply by 2. There's no other terms to worry about because the antiderivative at 0 evaluates to 0. And so the answer is simply 48. And for our last slide, I want to point out a potential question that would come to mind when thinking about average rate of change. In particular, let's talk about average velocity. We very often consider an object which has position s of t at time t and velocity v of t, which equals the derivative of position. Of course, v of t is the instantaneous velocity at time t, but we also talk about the average velocity over an entire time interval from a to b. And this we defined as the change in position divided by the change in time over the entire interval of time. So now that we have defined the average value for any quantity, you might be worried what we mean when we talk about average velocity. Are we referring to the old definition of average velocity, or are we talking about the average value of the velocity function v of t over the time interval from a to b? Well, as it turns out, these are just the same thing, because by part 2 of the fundamental theorem of calculus, the integral of s prime of t from a to b is just s of b minus s of a. That's part 2 of the fundamental theorem. And this is just the integral of velocity v of t from a to b. And everything here is divided by b minus a, still in the denominator. So this really does equal our definition of the average value of v of t over the time interval ab. So there's no confusion after all, because the average value of the velocity function v of t over our time interval does come out to be the same thing, exactly the same thing what we called earlier the average velocity over the time interval ab.